Okay, cool. Hi everyone, I'm Ben. I'm a grad student at Stanford. I work with Susan Clark on the interstellar medium. I'm also a member of the VIA collaboration, and today I'm going to tell you a bit of preliminary work on sodium tomography with hectashell. So what is tomography? Tomography is 3D mapping. So imagine taking these beautiful 2D maps we have of dust and gas in our galaxy and figuring out what they look like in 3D. And not only what they look like, but what they are. Like what's the density, temperature, velocities as a function of X, Y, and Z. This is very hard. We basically cannot do this directly, at least. And we've only been able to start doing this indirectly with dust in a small volume around the sun. But it's really important that we're able to do this because this is where all the physics is happening in this space. So whatever ISM question or physical model you want to test, you'd really prefer to be doing it in 3D space with physical quantities, not in 2D projection. And just to give you an example of some of what you might be interested in is the biggest scales, like what's the spiral structure of the galaxy? We kind of embarrassingly aren't even really sure if they look so like pretty spirals like this, and we need 3D maps to tell. Slightly smaller scales, molecular clouds and star formation. You know, where are they? What environments are they in? How is it related to the distribution of stars? How are the gas dynamics there influencing the timescale of star formation? And then even smaller scales, maybe you're interested in like dust physics. What causes dust grains to form? Like what radiation field is there? What's the gas temperature? All those things, you know, you can talk about this stuff in 2D, but it's really transformative, of course, to have another extra dimension, and the list goes on. So just to give you a little bit of an idea of the observational landscape, oftentimes if you just look in any direction, so this is in the plane towards the anticenter, you can measure gas through emission, usually integrated emission and absorption line. For example, the purple line, the light purple one is 21 centimeter neutral hydrogen emission, and it tells you total amount of neutral hydrogen at any given velocity that way. And if you're lucky, there might be a bright quasar there as well, and you could get like H1 21 centimeter absorption, which the lines tend to be narrower, and you can resolve all sorts of interesting velocity structure. But we don't really have a way to tell where this stuff is in distance space. And this is the same, there's plenty of other tracers, but you know, it's typical to only deal with integrated measures of density. By contrast, so I show you that other dust map, and there we're able to get, you know, thanks to a lot of good work by other people, dust extinction density as a function of distance. And that's done by looking at hundreds of millions of stars over the sky, calculating the extinctions, and as a function of distance, basically, and like taking the derivative with much more proper statistics, and then you can like, you know, start to see where all these dust peaks are. And it's big business to try to figure out which velocity peaks correspond to which dust peaks, because we have no other real way to get the gas distribution. But that's pretty challenging because dust and gas really aren't all that correlated, and we'd really like a direct way to do this with gas. So the pitch, what I've done, and this is with Charlie Conroy, is try to do the exact same measurement with the kind of level of stellar density for the dust mapping, but with sodium gas. So we took hectashell, pointed it here, so it's in the plane towards the anticenter, took like 600 brightest stars, just got stellar spectra for them. And this is what the raw data looks like. I've zoomed in on one of the sodium doublets. Yeah, okay, already you can see a big giant ISM component there. And then all these like horizontal, like noise looking stuff, that's the stellar sodium lines, which are contaminating our signal. And I've plotted these as a function of median Gaia distance, because we're trying to do it as a function of distance, right? And you can immediately see, you know, at any given point, the sodium absorption is kind of cumulative. It's everything in front of that point. So you can see a lot of interesting structure. For example, there's a big peak here starting at 700 parsecs, and maybe another one you can see at a different velocity at a little over a kiloparsec, which you know, is slightly promising. This is kind of where we see two big peaks in the dust distribution. Moreover, you know, you can see the velocity structure by, you know, additional components being added at slightly different, I would say I can kind of see 3 different steps in the velocity, which are around 20 kilometers a second apart, which I think you can start to convince yourself might be related to these 3 peaks in the H1 absorption profiles. But, okay, that's nice to do on like a cloud peak basis, but there's so much more in this data. We have so many spectra. If you look at the individual spectra, I just pulled out a few. Even in this beginning region, you're very sensitive to sodium, and there's already potentially some velocity substructure, even like in here, that we'd really like to get the maximum value out of the data. But if you look at so these are pretty clean spectra. The stellar lines are elsewhere. These are pretty complicated line profiles. They're not a Gaussian or even like 3 Gaussians fit together. Fortunately, we basically know exactly how those lines are formed. Out there in space, right, there's basically some neutral sodium density as a function of distance, and there's also a neutral sodium velocity as a function of distance. And if you have those 2 functions, you plug in radiative transfer and you can calculate the expected absorption line in a star at any given distance. So hopefully that kind of makes sense. There's also temperature, which we're not resolving the thermal broadening. It can affect the saturation, but we'll worry about that later. And this is not just, we know how to simulate these things, but that means we also have like a forward model for all of our data. And so what we do is we fit these functions jointly to all the spectra to produce kind of like synthetic data, which you can compare with the real data. Okay, I haven't shown like error bars and things, but it looks kind of similar. And maybe, and so this is a way in which we're going to try to measure the sodium density and velocity functions. The advantage, like why do we need to do this, is because this lets you do so much more. Like this lets you put a positivity prior on sodium. So if sodium appears in one stellar spectra, it better appear in a spectrum of a star that's further away, which helps with the separation. And it also lets you control in a more natural space what kind of smoothing you're going to do. So rather than how many Gaussians do I fit to the line, it's like, what's the power spectrum of like how smooth is the sodium in physical space? So I think it's a more natural way to think about it. Of course, so this is just the sodium, and I showed you these like very pretty stellar lines where you can see the sodium, but most of our data looks like this, right? It's giant. These are a lot of cool stars. There's big sodium lines from the star, and so star is yellow, and then it gets multiplied by the model from our whole like joint model of the sodium absorption line, and it's often like a tiny little bump on the side, or a broadening of the stellar line. So it's important to also like do a joint fit to all the stellar spectra as well. Yeah, but this is a little preliminary. I wouldn't, the stellar modeling is still a work in progress. But okay, and there's a bunch of other caveats here. I haven't folded in distance uncertainties, but that's something we can naturally do in this framework. Constant temperature, some rough stellar modeling, and big one, no plane of sky variations are assumed. So this is hectoshells 1 degree across. Nearby, that's a very small distance. So we can probably be safe. Further away, there's going to be significant sodium variation across the plane of sky. Remains to be seen how much we can learn about that, or what level of assumptions we have to make. I made this little movie of moving through space, like just like what is all the equivalent widths we're measuring after modeling out the star, and you can see there is variation. It doesn't look like there's big gradients. A lot of this variation can be explained by these stars are at different distances, so there's a lot of degeneracies that we have to still work through. But the basic point, you just look at the data, is clearly there is like the dominant effect is one kind of interstellar sodium distribution. Okay. And I think this is a nice sanity check. You can plot it over the dust, and you can see some level of correlation. We don't expect them to be exactly correlated at all, but this will be a main interesting thing to check once we're sure about the sodium modeling, is how does it compare to the dust. Cool. Okay, I do want to mention there's like a lot of prior work in this space trying to do 3D mapping of sodium, but it's all kind of these thousands of stars distributed over the whole sky. And so it really violates this assumption of they're all along one line of sight. And so people have tried to make maps in small volumes, which you can see big kind of molecular cloud complexes, but these models are really not consistent with the data. They're quite over-smoothed. And they also don't attempt really to do this kind of like fine-grained velocity mapping, which I think is one of the most exciting things we can do with sodium. Sodium doesn't tell you the hydrogen density, so the sodium density isn't as interesting as the sodium velocity, which is definitely the same as the like bulk hydrogen velocity. Yeah, so there's prior work, but I think nothing at this kind of like level of detail along a single sight line. And yeah, and so I'll have one more slide. So it's not Thursday yet, but just to mention a little bit about VIA. So we're very lucky to be able to do this in the like basically final few weeks of Hector Shell's life. But VIA will be able to do everything I just showed you in 10 minutes. So we can think more ambitiously. This is a hypothetical, but we can really afford to do a map of the 3D map of the velocity in the plane with VIA. Do some specific regions or like look at every H1 absorption sight line. So it's all very exciting. Yeah, so I think I'll end it here and ask for questions early so we can go to lunch.
Igor. So in your plots, you can always see lines, often see lines going down to zero, which means that they are saturated.
Oh yeah, yeah.
And so, did you think about using any other tracers to verify, like I know potassium or calcium 2 or something like this?
Yeah, so we did not have time to do that. Would have been great. Also this is prep for VIA. There is data we're looking at that has these lines that we would like to check. So that's a great idea. But I would just also note that we are like taking into account the saturation effect, like we're doing the correct rate of transfer in the model. Yeah, but good point.
Great talk. I'm curious, what is the resolution of the spectra that you have? And would anything be gained going to higher resolution and looking at these stars using like R of like 10,000 or something on like a real big shell spectrograph?
Yeah, so this is Hector shell, so it's 35,000, which is important. I mean, you can contrast this. There is a lot of work with lower resolution multi-object spectrographs that can do some of this work, but really not the key thing is like the velocity resolution. So we've tried the SNR to try to get to like a 1 kilometer per second. And we are looking at some kind of potential higher resolution sources, but like we're already a pretty good resolution. That's the plus of this, I would say, yeah. And a plus of VIA.
Yeah, I had a question about the distance resolution in your tomography. So I was wondering if it's driven currently more by the uncertainties in Gaia distances or parallaxes, or by just the sampling of kind of how many stars you have at
Yeah. I think in the beginning it's the sampling. It's just a degree nearby is not fewer stars, and then at the end it's the Gaia distance for sure. And we can probably benefit from, we have pretty good spectra. We should be getting better distance constraints from the spectra than the parallax, but I haven't done that, and I'm not exactly sure. Probably around 800 or kiloparsec it's changing over.
So will the strategy with VIA allow you to have more densely kind of populated field closer in to maybe increase that resolution closer in?
Yeah, exactly. I think the strategy with VIA is that we can like move much faster, so we can cover wider area, which is what you need to do to get all the bright nearby stars. Yeah.
Great, thanks.
Okay, so if there are no more questions, let's thank Ben again.